Hello, students. Well, we're finishing Chapter 9. The end of Chapter 9 is about something I'm going to call COM. What does that mean? Well, this red dot is the COM. You see, the red dot indicates the location of the center of mass. So if I have something spherically symmetric, like a baseball, the center of mass is right at the middle. But if I have something that's, let's say, skinny at one end and fat at the other end, like a baseball bat, the center of mass, the location of it, is going to be shifted a little bit towards the fat, the more massive end. You see, there's more mass at this end than the other end, so the center of mass shifts. The center of mass of a triangle like this, you can figure it out using geometry. The center of mass of a three-dimensional object like this is buried in the middle of the object. Figuring out the exact location would involve a little bit of calculus. Okay, now one way of thinking about center of mass is it's the balance point. So if I were to put my finger underneath the baseball bat, it would balance if I put my finger right there. If I put my finger underneath a triangle, if I put my finger there at that location, it would balance there. Let me show you a trick for finding the center of mass of an object. Okay. Now, where's the center of mass of this pipe? Well, here comes the trick. I'm going to put my fingers at both ends and gradually bring my fingers together. And there we go. There. Okay, the center of mass is right there, which happens to be the center of this pipe. No surprise there. That's the balance point of the pipe, the center of mass. Okay, so why do we care? Well, here's sort of a preview of why. Okay, if I'm throwing something like a baseball, the baseball being spherically symmetric is going to do what we expect: simple projectile motion described by Newton's laws, and it's easy. But if I want to figure out the motion of a baseball bat, which has this funny, the center of mass is not right at the middle, it's going to be complicated, especially if I pick a spot like right at the handle, right? The handle is going to do some really complicated loopy motion, and that's hard to describe. But if you don't mind just sticking with the center of mass, then the center of mass of the bat, right, this spot here, it's going to do nice, simple, parabolic projectile motion. So let's move on now, and let's see. So basically Newton's laws for big, complicated objects, those laws work okay if you just use the center of mass of those objects. So Newton's second law, right? So for just a particle, we would say, okay, F equals ma. But if you're now talking about some big extended object, it could be a satellite, right? The NASA is interested in things like that. The motion of the complicated object, it is going to follow Newton's second law in this form. The overall force applied to the object is going to equal the mass of the object times the acceleration of its center of mass. The momentum vector of the big object is going to be the mass of the big object times the velocity of the center of mass. Okay, so you see there's a lot of simplification that can happen. It turns a complicated problem into a much easier problem. Okay, so now let's find out about where the center of mass is. So I'm going to teach this by just starting out with an example. Suppose you have three equal masses, mass 1, mass 2, mass 3. And each one, to make this example simple, I'm going to make each one equal mass, although I didn't have to. The formulas here are going to work regardless, but let's just make it equal mass. And so the basic mass is m0. So mass 1 has mass is equal to m0. The mass of m2 is m0. The mass of m3 is m0, let's just say. Okay, now here is the basic formula, the important one. Here, let's highlight this guy. The location of the center of mass is given by this formula. It's going to be x1 times m1 plus x2 times m2 plus x3 times m3, all divided by the sum m1 plus m2 plus m3. And oftentimes I use a shortcut, just write down big M to mean m1 plus m2 plus m3. Now, I stopped at 3 masses, right? But really this formula continues. Let's say I had 4 masses. Then I would have to do x4 plus m4. And then, of course, down here in the denominator, this would also be plus m4. Yeah. Now, so now using our example, x1 for mass 1, oh, it's at -1 meter. So you see I'm going to put -1. Now mass 1, I said, for simplicity, is equal to mass is m0, okay, that many kilograms, whatever that is. Okay, mass 2, its x location is 1 meter. Okay, so I put 1 times its mass, m0. And mass 3 is 1, 2, 3 meters over. Oh, okay, so it's at 3 times m0. And each one weighs m0, so it's 3 m0. Now, the m0s cancel, okay. And so I have -1 plus 1. Oh, that's canceling. Okay, 3 over. So the center of mass is at 1 meter. The x location of the center of mass is somewhere along here, okay, along x equals 1. Now we can go through the same process for the y location of the center of mass. So the y coordinate is 0 for mass 1, so I have a 0 there. The y coordinate is 2 meters for the second one. It's 0 for the third one. So I have 2 over 3, and so I get 0.66 meters. So the location of the center of mass is at y equals 0.666 here, okay, somewhere along here, and x equals 1, blah, 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 and that means the center of mass is right there, okay, I'll do it in a different color. There, that's where the center of mass is. Okay. Yeah. So here we go. Now, I want to do a little demo here, and before I do the demo, let's suppose that I had, let's say each one of these objects was an extended object. For example, let's suppose that mass 1 was this pencil, right? And it was like this. Let's suppose that mass 2 was this pen, right? So it was, let's say, like this. And let's suppose that mass 3 was this pen, okay, like that. And I ask the question, where is the center of mass? Well, each one of these things has a center of mass of its own. So the center of mass of the green pen is, probably close to the middle of this green pen, unless one end is much heavier than the other. The center of mass of the red one is probably right there, and the center of mass of the pencil was probably right there. So if I want to ask the question, where is the center of mass of a system with these three objects, then I can do it by finding the center of mass of each one of these objects and then working out the math. Okay, so I have here for my demo a foldable meter stick, right? And if I fold the meter stick like this, where's the center of mass of this thing? Oh, it's right at the halfway point, right? Where's the center of mass of this part of it? Oh, it's right at the halfway point. But now, where is the center of mass of the overall object? If you want to stop the video here to think about it, you could stop. Okay, I am going to reveal the answer. And it's a surprising answer. It's right there in space. You see, the center of mass of an extended object doesn't have to be in a place where the object is. It could be like between the legs, right? The center of mass of, let's say I somehow were to fuse these two pens together in some invisible force field, you know. Well, the center of mass would be like right there between them. Yeah. Now I can prove to you that the center of mass is right at the center by doing this. You see, what I've done, I've got another one. I happen to have two of these meter sticks. And what I've done is I've made a little contraption here where I can hold this meter stick right by the center of mass. What I've done is I've got a little chopstick here and a rubber band, and the rubber band is going to be at the center of mass. So here we go. Let's see if we can get this to work. This may be a little fussy. A bit further over to the left. It's a little too far to the left. Let's go back a little bit more. And there you go. It's not quite perfect, but there you go. All right. Now that I've got this going, I want to tell you something else that's important about the center of mass. Whenever something spins in space, something like a satellite, right? NASA, wants to know where the center of mass of their satellites are. And the reason is that satellites and just about anything that's sort of like floating is going to spin around its center of mass. See? So if this were a satellite in space and it were spinning, and most satellites have a little spin to them for stability, it would spin around that location. Another application of this, in a washing machine. I don't know if you've ever looked down into a washing machine when it's on the spin cycle. You're not supposed to, right? Because it's dangerous. Like you might put your hand in there when it's in the spin cycle and then you get your hand ripped off. But anyway, let's say you defeat that and you can manage to look. The tub of the washing machine, when it's spinning around its center of mass, and the center of mass is usually not right at the center because you might have a pair of blue jeans over here and a wet towel over there, and so the center of mass is a little bit offset. The machine manufacturers, the washing machine manufacturers, deliberately make it so that the tub can kind of loosely, easily float around a little bit. And they do that so that when it spins, it'll spin around its center of mass, and it'll actually go quite smoothly, just like that thing was spinning nice and smooth. If the washing machine manufacturers decided to put a really strong post in the middle and force it to spin on its axis, the washing machine would be jumping all over the place. You don't want that to happen. Okay. So, anyway, let's move on. Yeah. All right. Okay.
Now what about the velocity of the center of mass? Let's go back to the previous example, right? I have my three masses, and let's say mass 1 happened to be moving in the y direction. Mass 2 happened to be moving partly in the x and partly in the y direction, and mass 3 were going in the negative y direction. Okay, well, it's easy to figure out the motion of the center of mass. Here is the formula right here. You want to know this formula, right? And yeah, over here is sort of like the shorthand version of that, the mathematical shorthand. Okay, so in words, the velocity of the center of mass is the velocity of particle 1 times its mass, plus the velocity of particle 2 times its mass, plus the velocity of particle 3 times its mass, all divided by the overall mass. So yeah, I've got a little example here, and so I put in some, let's suppose, okay, so I made my example match my drawing here. Let's say velocity 1 is 0 in the x direction, right? It's not going in the x direction. And it's going 2 meters per second in the y direction. Let's say particle 2 is going at 45 degrees, 1.5 meters per second I, 1.5 meters per second J. Yeah. And let's say this is the velocity in the negative y direction of particle 3. What is its center of mass? Well, you just plug and chug, right? You just put the numbers in. So we've got 0I plus 2j times I'm assuming, just to make my life easy, that the three masses all have the same mass. I'm calling it that mass 0. And so you end up with, okay, let's look at what the i's do. So 0 plus 1.5 plus 0 is 1.5. Okay, so it's 1.5i dividing by 3. Yeah, there's canceling going on here, right? Cancel. And in the j dimension, I've got 2 plus 1.5 minus 2.5. That comes out to 1. And so I have 1 in the j direction, in the up and down direction. And so, okay, so in the end, we have 0.5i and 0.333333j. So the center of mass velocity vector would look like that. And it has dimensions of meters per second. Right? So it's up and to the right. And so, yeah, okay, the combined center of mass. So here's the center of mass, and it's moving like that. Notice I didn't draw it at the same angle. It's at a lower angle because the up part is partially canceled by the down part of this third particle's velocity. Okay, so that's the velocity of the center of mass. And then, of course, you could have acceleration of the center of mass. And so, yeah, here we go. Here is the formula for the acceleration of the center of mass. Okay. And I have yet another example. Let's say particle 1 is not moving and particle 2 is moving to the right at this speed, 5 meters per second squared, acceleration, 5 meters per second squared. And particle 3 is accelerating downward at negative 10 meters per second squared. And so I plug in my numbers. I think you guys know what's happening by now. And I get my answer. Now, I kind of alluded to this earlier, but let's say it once again. Newton's second law can be used to figure out the motion of the center of mass of an object. So if I know the forces on the satellite or whatever it is, and I add them all up and I get the overall net force on that object, right? So maybe I should have put F big object net, right? Okay, got lazy there. And then I divide by the mass of the overall object, I will get the acceleration of the center of mass. I'm using the book's convention here. I'm using capital A to stand for the center of mass acceleration. And if you noticed before, I used capital V for the center of mass velocity. And yeah. Okay. Now, coming back to the topic of the chapter, actually, the momentum. You see, the velocity of the center of mass is the velocity of the first particle times its mass. So that's the, let's use red. So this piece here is the momentum of particle 1. And this piece here is the momentum of particle 2, and so on. And then, so I'm taking the total momentum, I'm adding up all of the momentums, and then dividing by the total mass right here. So this formula here should feel familiar, right? You've seen this formula before. The velocity of some particle is its momentum divided by its mass, right? And so this formula is coming back now, but it's coming back for the overall big object. So if I have a big object, a satellite or whatever, a car, its center of mass velocity will be its total momentum divided by its total mass. Now, this is a rock solid statement, and it's solid. It's true even in some surprising circumstances, namely explosions and crashes, things coming apart together and apart. So just as one quick example, and then we're done, we have, let's suppose that I had let's say this is happening in space, right? There's no gravity. And I have a firecracker, and it's moving along. It's going bum, 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 right? Its motion is like this. And when this firecracker gets to this location, it explodes. And when it explodes, the pieces go flying apart. Let's suppose, just for simplicity, that it breaks into two parts. So part 1 goes this way, and part 2 goes this way. Well, if I add up here's a diagram. This represents the original momentum, and then it breaks, and so now it had the two pieces. Okay, piece 1 has this momentum vector, and this piece here has this momentum vector. If I add up these two momentum vectors in the diagram here, we're adding using the tail-to-tail method. So when I add these up, I get that the total momentum is this. So here it is. The final momentum is this thing here. And the law of conservation of momentum applies. This initial momentum is the same as the final total momentum. And so this can become very useful. It can make complicated problems much simpler, and so you're going to have some practice doing that. Okay, so I'm going to stop here.